for colloquium for us, and she is talking about the locally primitive universal form, primitive counterpart of the 15th. Please welcome Lakshika.
Thank you for the introduction, and I would like to thank to the Department of Mathematics for the opportunity, and I would like to thank my advisor, Dr. Ernest. So today I'm going to present some interesting results we found when we are working on primitive representation. So my topic is locally primitive universal forms and the primitive counterpart of the 15th theorem. So first, let's try to identify what is a quadratic form. So it is a homogeneous quadratic polynomial with n variables. By the name quadratic means the degree 2, so you're familiar. So there are some famous historical results we can see from quadratic forms. So Fermat's theorem in 1637, he presented some quadratic forms like in two variables, x squared plus y squared equal to any integers, like the Pythagorean triples and elliptic curves lies into this form, two variables. And Gauss three-square theorem in 1801, and this addressed the problem which integers we can represent like a sum of three squares. So, and also there's given some specific form, which type of integers we cannot represent as a three square, a sum of three squares. And we have famous Lagrange's four-square theorem in 1770. So he proved that every integer, every positive integer can be represented as a sum of four squares. And this has an ancient history, like Brahmagupta in 628. He studies quadratic forms of the form x squared minus ny squared equals c. When c equals 1, we have Pell's equation. And the father of number theory, Ramanujan, in 1970, he presented a list of forms which represent all positive integers. So these forms we call diagonal forms. I will call y later. So then this continues, and in 1938, Hermos presented 88 forms of the same form but with one exception. Alright, so quadratic forms has some applications in various fields. In mathematics, I can give explicitly in number theory, projective geometry, and algebraic topology, etc. Right? And also, it is used in coding theory, cryptography, physics, engineering. Okay, now let's identify what is the formal definition of an integral quadratic form. An n-dimensional integral quadratic form over C is a polynomial of the form x consists of n variable as a summation aij xi xj, where I and j is between 1 and n. And here we have another condition added. Aij is the same as aji. So in this, with this condition, we can see the cross terms of these quadratic forms will have even coefficients. So for a given dimension, to identify a quadratic form, it is enough to have an idea about the coefficients. So that's why we can denote a quadratic form using a matrix. So if we denote if we let n vector denote the matrix Aij, the coefficient matrix, you can see this will be a symmetric matrix. We call it a Gram matrix. And also the determinant of this matrix is also defined to be the determinant of the quadratic form F. So we can just define the determinant of F in terms of this matrix. And through this study, I am going to talk about positive definite quadratic forms. So an integral quadratic form is called positive definite if for any non-zero vector, the f of that vector is greater than 6. Then it is called the positive definite quadratic form. Okay, now let's see what is called a representation over C. To understand this, I am going to use an example. So suppose we have a 4-dimensional quadratic form given by sum of 4 integer squares, like x1 squared, x2 squared, up to x4 squares. So can we find integers gamma 1 to gamma 4 such that f of these integers equal to 9? If I ask, you may have different answers. You can let x1 to be 3 or x1 to be negative 3. Likewise, actually it has more than one solution. But the solution or number of solution of this problem is finite. It's proven to be a finite problem. So here are some examples we can have. We can let x1 equal 3 or x1 equal negative 3, or maybe x1 equal 2 and x2 equal 2, x3 equal 1, likewise. Okay. Now let's see what is the formal definition of the representation. The same idea, now we can denote in this way. If we take any positive integer alpha in n, so we say the integral quadratic form f represents alpha over z if there exist integers gamma 1 to gamma n such that f of gamma 1 to gamma n equal to alpha. Or we have to find integers to satisfy the given quadratic form. Okay, in symbols we denote it as alpha arrow f.
Lakshika, maybe are you always allowing? Do you always allow the solution with zeros, or do you especially just sometimes exclude the case with the zeros?
Without zeros?
Yeah, somehow.
It's okay.
It's okay.
We can have zeros. But we cannot have all zeros, like just the zero representing 0 will be that. But in this solution, that's fine.
Okay.
So there are some examples and some studies on representation. As I mentioned, Lagrange's four-square theorem. So he showed that every positive integer is a sum of 4 integer squares. So you can see that means, so we can denote any positive integer using that quadratic form given by sum of integer squares. So when a quadratic form denotes every positive integer, represent every positive integer, we call that quadratic form is universal. So that is the definition of a universal quadratic form. And in 1917, we find an interesting result, as I mentioned earlier, by Ramanujan. He asserted that the following list given here are the only universal diagonal positive definite quaternary form. Quaternary means dimension 4. So here, when we think about this, how it goes, the argument is not that difficult. That's what I have here on this board. So if you have this diagonal form like this, with this condition, let's use this condition where with this order for A, B, C, D coefficients. Now, if we need to denote or represent 1, we have to have A equal 1. Otherwise, we cannot denote 1. So, if A equal 1, so B has to be less than 2. If it is 3, we cannot denote 2, so it has to be less than 2. So, it should be between 1 and 2. Now, when it is between 1 and 2, we have two cases, could be 1 or 2. When it is 1, again we have conditions on C. So C has to be less than 3, otherwise we cannot denote 3. Likewise, then we have 3 cases for C, and here we can have more conditions on the next coefficient D. So, in this way we can check, we will get all of these 55 forms in these branches. So the most interesting thing here is how to prove these are the only universal diagonal forms, or which are universal, or how to prove this is a universal form, like this. So And also you can see the first one is actually corresponding to the Lagrange's theorem. This is when we have sum of 4 integer squares. And here, when we take one quadratic form from this list, if I ask you how to check whether it is going to be a universal form, so that means how to check whether it's going to represent every integer. So how we are going to check? Are we going to check from one by one? So it's not going to be a finite problem anyway. But now if we think about this, we have some interesting or important or fascinating tool called 15 theorem. So in this case, we can make such a problem a finite problem. So this is called 15 theorem, given or presented by Judge Conway and Schneeberger in 1993. They proved that if a positive definite integral quadratic form represents every positive integer up to 50, then it represents every positive integer. So that means if a quadratic form can represent just 15 numbers, then you can conclude it represents every positive integer. So it is actually, you have to check just 15 numbers. So you are done. So it's a finite problem. So this is actually the foundation of our study. Okay, so later, Bhargava in 2000, he also gave a refinement to this 15 theorem, and he proved that now you don't have to check the 15 numbers, just 9 numbers is enough. So all you have to check is whether this form represents 1, 2, 3, 5, 6, 7, 10, 14 and 15 only. So if you can represent these 9 numbers, then you can conclude that is a universal form. Okay, so the first theorem, 15 theorem, the proof was never published, I think. So that's the thesis for Schneeberger. Later, the Bhargava gave an easier proof for the 15 theorem. So that's the reason why the original proof never published. Okay, so Bhargava didn't stop there. So he continued his study on this, and using this theorem, he proved that there are exactly 2 or 4 equivalence classes of universal quadratic forms, and presented the list I will give you in the next slide. And there, in that list, you will see there are just numbers. Those are the coefficients, and also that will give you a quadratic form of this form. So this is the list. For example, if I take this third one, where we have 3, 1, 2, 2, 2, 0, 0. This will give you a quadratic form A with x0 square and x1 square, 2x2 square plus 2x3 square, and this is the cross coefficient 2x2, x3. And the determinant of this quadratic form is 3. This is that number. So that is how you read this list. So studying or theory of representation is being used by many mathematicians over the years, and the theory of representation has many fields: almost universality, primitive universality, universal forms over totally real number fields, higher dimension analogues of universal forms, or universal forms. With this, we are interested in primitive universality. So I am going to introduce what is called primitive representation. A positive integer alpha is said to be primitively represented by an integral quadratic form f if there exist integers gamma 1 to gamma n with GCD of these numbers equal to 1, such that f of gamma 1 to gamma n equal to alpha. So you can see this is similar to the definition of representation with one additional condition. Now we have to have GCD of this number to be 1. I will give you an example to understand the concept. So again, I'm going to use the Lagrange's theorem. So Lagrange's quadratic form here, sum of four squares. So we saw that when we have f of 2, 2, 1 and 0, it is equal to 9, and also the GCD of these numbers equal 1. So this means 9 is primitively represented by this quadratic form. And when we try to get a primitive representation for 8 for using this quadratic form, we cannot do that. You can check. We can let x1 to be 2, x2 to be 2, like 4 and 4, but you can see the GCD is not going to be 1 in this case. So it's not going to be primitive. So when we have, for a given quadratic form, the smallest integer where we cannot denote primitively is called the primitive truant. So in this case, 8 is the primitive truant for this quadratic form. Anything up to 8 can be represented primitively. Okay. So we stated the universal forms earlier. Similarly, we can define primitive universal forms. When we have an integral positive definite quadratic form which primitively represents all positive integers, then we call that form is primitively universal. And the same way, we can denote almost primitive universality when it represents all sufficiently large integers primitively. Right. So in here, in our study, what we are interested in, so you remember the 15th theorem, we have a quadratic, if we have given a quadratic form, if we can check whether it represents all 15 numbers, then we can conclude it is universal. So here what we need, what we want to show that if we have a quadratic form, is there exists a set, a finite set, so we can check these numbers and conclude that it is primitively universal. The same thing for the primitive. So we were able to prove that there exists a finite set S, so that is guaranteed. There exists a finite set. But all we have to prove is now, or all we have to find is what is the set? What are the elements of this set? So this proposition is already proved. There exists a finite set S of integers such that if a positive definite integral quadratic form primitively represents every element of this set, then it is primitively universal. So let's try to find this set. We want to find that set. Okay. So our aim is to find all primitive universal forms in 204 list and to find all possible primitive truants. So that's where we started. So what we were doing was we considered 204 list and we tried to identify all primitively universal forms in this list. And if we can find any truant for a given quadratic form, then we can conclude that is not going to be primitively universal. So fortunately there were some studies done previously on this topic. So the first thing we find in 2010 by Gunawardana. So before I go to the theorem, I will introduce what is a genus is. So when we have an integral quadratic form, the genus of this form F is the set of all integral quadratic forms G such that G is equivalent to F over Cp for all for each prime P, and it is equivalent over R. So then let's come to this theorem. So what she has proved, if there is a positive definite integral quadratic form of dimension at least 4 with odd square free determinant, then F is an almost primitive universal form if it primitively represents every integer in the set 1, 4 and 8. So what it says, so if you have a quadratic form more than 4 variables and if you have the determinant of this quadratic form is odd square free type, then if you can check whether it represents 1 for 8, will guarantee that it is almost primitively universal. So whenever a quadratic form is almost primitively universal, and if it is unique in its genus, then we can say, or we can conclude, that is primitively universal. So in this way, she was able to identify primitively universal forms in 204 list. And also, you can see there are some restrictions here. You have to have odd square free determinant, and it has to represent 1 for 8. So when we were looking at this theorem, we found what happened when it is even square free determinant. Then we found it is the even case is even easier. So in this case, we proved that even square free determinant need to represent just an odd number. That is enough. So actually we were able to combine these two and come up with the general theorem for this one. Anyway, so in her study, Gunawardana studied square free determinants and odd and even both. So finally she identified 10 primitive universal forms in 204 list. So these are already identified, so we don't have to worry about these 10 forms. So these are clear. So the next study we find in 2014 in a study of diagonal forms on strictly regular diagonal forms by Dr. Ernest, Young Kim and Nick Mayer. So there they proved there are 96 inequivalent positive definite diagonal quaternary integral quadratic forms that are strictly regular. Among these, 34 are in one class genera, that means they are unique in their genus, and 27 are primitively universal. So this is what we are interested. We have 27 forms proven to be primitively universal in this 204 list. So here we have identified 27 forms. Earlier we had 10 forms identified. However, some of these forms were identified in both studies. Finally, we have 34 primitively universal forms, which has identified already. So it leaves 170 forms for us to check. Okay, so all we have to check these 170 forms in the 204 list. So what we used was the software called Sage and checked each up to 400 to check whether we have any primitive truant. If we have a primitive truant, then we can conclude that is not primitively universal. So out of these 170 forms, 97 gave primitive truants and leaving 73 forms without any truant up to 400. So we can see these 97 forms are not primitively universal. Now, these 73 forms, we do not have any truant up to 400. It does not say these are going to be primitively universal still. So this is where we have to give theoretical proofs, whether it's going to be primitively universal or not. If we can prove these are primitively universal, then we will be able to prove our whatever the result is. Okay. Interestingly, when we think about these 97 forms which gave primitive truants, we identified that there are limited number of primitive truants, and when we check up to 400, the highest truant appears for 64. So just 11 numbers and highest being 64 gave us like an idea. So these are the only truants we can have for all of these quadratic forms or in the 204 list. So we combine this result, these 11 numbers, with the earlier 9 critical numbers given by Bhargava to come up with this conjecture. So now we think this, we claim if there is a positive definite integral quadratic form which primitively represent these 20 numbers, then it should be primitively universal. So we already proved that there exists such a set, so we claim this is going to be that set. So still we need to prove that. So as I mentioned earlier, there were 73 forms without any conclusion where we have to give theoretical proofs. So we were able to prove 28 out of these 73 forms to be universal, primitively universal, but still we want to prove the rest to come up with the primitive 15 theorem for the quaternary integral quadratic forms. Okay. So this everything up to this point we talked about universal forms and primitively universal forms. Now to give my next result, I am going to introduce almost universal forms and almost primitively universal forms. Okay, a quadratic form F is called almost universal if it represents all sufficiently large integers. So that means you don't know what is the limit, but up to some point, after some value, it's going to represent every positive integer. So that means you are going to miss only a finite number of set, which is not going to be represented. Okay, the same way we can denote almost primitive universality. This means when you can primitively represent all sufficiently large integers. The same way, now we need the primitive representations in this case. So there were some studies done previously and some historical approaches in almost primitivity also, and almost universality. In 1970, with his studies, Ramanujan proposed and partly solved the problem of determining all diagonal forms in the given form ax squared plus by squared plus cz squared plus dw squared, which represent all but finite number of positive integers. So there he introduced this problem, the almost universality. Now in later 1926, Klusterman solved this above problem given by Ramanujan, except for the four of these forms given. And after that, in 1945, Hall completed the problem of this Klusterman's problem and gave a criteria to identify periodic universality of diagonal quaternary forms. So this is important. So he gave a criteria to identify periodic universality of diagonal quaternary forms. So I will talk about this periodic universality later. And then in 2008, Bochnak and O presented an effective method to decide whether a given positive definite integral quadratic form represents all large positive integers. So this fourth one is important. So it is not just about diagonal forms now. It's about any quadratic form. You can have cross terms in this case. So they have given this effective method to decide whether it is going to be a almost universal form or not. Okay. So in order to identify almost primitively universal forms, it is important to identify what are CP universal forms. To get there, I am going to start with introducing p-adic numbers. I will do a quick review on this. So let's try to identify what is a p-adic norm. Okay, when we take any non-zero rational number, then for a given prime, we can write x as a power of p times r over s, where r and s cannot be divided by p, and a is an integer. Now we define p-adic norm as p to the negative a. That's the highest power. And for the zero, it is defined to be 0. That's the initial condition. For example, let's take this rational number x equal 24/25. So you can see we can identify prime powers in this number. 2 cube times 3 over 5 square. Now when we consider the two-eddic norm of this number, it is going to be 1/8 because that's the power of 2 we have here. And when we consider the triadic norm of this number, it is 1/3. And 5-adic norm will be 25, which is 5 to the negative 2. So, and the 7-adic norm is going to be 1 because we cannot see any 7 here, the factor. Okay. So, this p-adic norm obeys to the usual norm axioms, but instead of triangle inequality, we have the strong triangle inequality here. And also the p-adic metric induces the topology on Q. You may have seen this QP. This is the field of this field is the computation of rational numbers Q with respect to the p-adic norm. If you have any numbers or any element in QP, this can be written in a unique way as a summation AI pi, where this AI is between 0 and p minus 1. This is called the canonical expansion of a p-adic number. For example, if we take x to be 240 in Q7, then we can write x as powers of 7 in this way. 2 plus 6 times 7 plus 4 times 7 square. Now we can see this is the canonical expansion. Now you know that we identify integers in rational number set. Likewise, we can identify integers in QP also. We can use the norm to identify the integers inside QP. The ring of integers denoted by CP consists of the elements in QP such that the norm less than or equal to 1. So if you remember the strong triangle inequality I have mentioned earlier, if you take the norm or p-adic norm of this number, this element, you will see this is going to be 1 actually, because that will give you the maximum of norm of 2. Norm of this number. This is going to be x7, which is going to be less than or equal to maximum of 2 and maximum of 6 times 7 and 4 and 7 square. So these are going to be less than 1. This is the one you will have equal to 1. So this is going to be 1 exactly. Okay, so fine. Okay, so if you have this norm equal to 1, then we can see there is a unit in CP. In this case, this 240 is going to have norm equal 1, so this is going to be a unit in CP. So now we have enough background to identify a CP universal form. So let me introduce what is called a primitive CP universal quadratic form. A quadratic form in CP is given by as a summation of aij, xi, xj, where I and j is between 1 and n, the same way. But now we have to have these coefficients aij is in CP, not just any integer, just in Z. So if F primitively represents each alpha in CP with at least one of these xi is being being an unit, then we call this is primitively CP universal form. So when you choose integers to represent a given number, you have to have at least one of these integers in CP to be a unit. In this way, you can identify whether this representation is going to be primitive or not. So how to check? This is a problem because we do not have a given criteria or effective method to identify whether a given form is primitively universal or not. But you can use some strategies and some tricks to check this. If we have enough time, I can go through that. Okay. So anyway, so let's move to the next one. So for this primitive universal forms and almost primitive universal forms also, we can find some interesting results. So let me recall the definition I have given earlier, that a quadratic form F is called an almost primitive universal if it represents all sufficiently large integers primitively. We have another definition for this one given by this theorem, which is interesting because we can use this definition for our computations. So it says every positive definite form of 4 or more variables is almost primitively universal if and only if it is locally primitively universal. So if you have given a quadratic form which is locally primitively universal, then you can see this is going to be almost primitively universal. So what does this mean by locally primitively universal? It means you have to have this quadratic form primitively universal at each p, at each prime. So if you consider CP, so you have to prove that is going to be primitively universal or primitively CP universal at each p. So does it sound like a finite problem? Like, can you check at each p? So one might say it's not going to be a finite problem, how you can check at each p. But we have a solution in the same book. So this theorem is again an interesting result we have. So if you have a quadratic form with determinant d, and if p does not divide d, then f is primitively CP universal. For example, if you have a quadratic form with determinant 6, so everywhere else except C2 and C3, it is primitively universal. So all you have to check is C2 and C3 only, whether it's going to be universal in these two.
Lakshika, when you say the locally primitive universal, you don't need to worry about the over real number because
that is when okay, that is P infinity.
yeah, yes, that's why.
I don't remember this theorem, whether it says anything about the real numbers. But locally primitively universal means C. Okay. Yeah, I'm not sure about that. I will check and
Yeah.
Okay.
Thanks.
Alright. Thank you for that point anyway. Okay, so when we were thinking about this result and when we studied and we continued this study on almost primitive universality, and we found some new interesting result here. The first one we came through is if a positive definite integral quadratic form is almost primitive universal, then it non-trivially represents 0 over Cp for all primes p. So this is so technical. This is not the one we are most interested in, this one, right? So a positive definite integral quadratic form in at least 5 variables is almost primitively universal if and only it is almost universal. So this is an important result. I will explain why. So you can see if you have any quadratic form with more than 5 variables. Now in this case we say that if it is almost universal, this is going to be almost primitively universal as well. So this means if you have more than 5 variables, almost universality and almost primitive universality, there is no distinction about these two. So when you consider the local computation again, like in CP, I mean this way. So when you consider CP, if you have a form with more than 5 variables, so if it is going to be, if it is universal, then it is going to be primitively universal as well. So there is no distinction when you come to CP if you have more than 5 variables. So this is very important result we found. So I think it's interesting. So we have further studies. We are going to classify almost primitively universal forms. So in a way that if I go back to this one. Oh, sorry. Okay, this one. So you can see I mentioned that here these two results, they have identified a criteria and a method to check whether given form is almost universal. So you can have a form and you check some conditions or criteria here and you conclude that this is almost universal or not. Likewise, what we need now, what we are going to prove, what we are up with is for the almost primitively universal form, can we do the same? Can we come up with a criteria or efficient method so we can check some conditions and conclude whether this is going to be primitively universal or not. So you can see with our previous result, for dimension greater than 5, these almost universal forms and primitive universal forms are the same. So most of the work has done. So what we have to check is for the dimension 4. So if we can find a better criteria for dimension 4, then we can easily classify the almost primitively universal forms. And for the 204 list, we have already classified the primitively universal forms, whether it's going to be a primitively universal form or not, but we need to find a general argument. Okay, do we have enough time? So I think I can stop there. Or
Okay. Do you have any question for Lakshika?
This big set S, is it going to be unique, or perhaps there could be different?
you mean
The
the
S
set?
which decides the S, we call it S.
That means the 20 numbers?
Yeah.
Yeah, that's what we claim, like for any dimension, we are going to prove that there is going to be just these 20 numbers if we can.
And that cannot be replaced by other numbers of the same size, the whole set?
Because those truant has to be there, because at least, because those truants means some forms does not represent that number. So it will be there, and the 9 critical numbers are from the Barger's list. So it has to be there in order to represent.
Mm-hmm.
So the 11 numbers for primitivity, I think this has to be there. What we can do is maybe we can add more if there's any when we come to higher dimensions. It's going to be reduced anyway.
Maybe did you use PAD method to prove the last 2 theorem of you guys?
I'm sorry.
And the last 2 theorem you showed that, and then did you use the PAD method or?
Yes,
move on to
yes.
the
When we
yeah.
proved that the result for the dimension greater than 5, so for the odd prime, it was very easy. It was very short proof.
Okay.
But when we come to the even prime, which is p equal to, that has the more work, like so many work in there. So odd case, odd primes are always easy. The
Okay.
p equal to is the problem, always problematic prime.
Even number 2. Okay.
Yeah.
Even number 2 is odd. actually.
Yes.
The oddest prime.
Yes, the odd is right. Any other question for Lakshika?
Is there any way to write it down in the matrix format?
For a quadratic form, yes. Shall I do it here? So, for example, I will use so f equal x sorry. Okay, 3b x3 and 2x1 x2 something like that. So this has dimension 3. So you can see this is going to be this coefficient. These are diagonal. So this is 1, this is 3, and x1, x2 is going to be here. When you write the gram matrix, you have to write it like half of this coefficient. The rest will be 0. Like that.
And then how this can be, helping you in your proofs make it, I don't know, I'm just thinking more generalization.
Yeah, we actually use these forms, like we call them lattice form, corresponding to a given quadratic form. So usually we work with these type of, for a given quadratic form, we usually work with like matrix or lattice form. So it is easier for us to work with this.
Yeah, that's what they thought.
Yeah.
And the way she defined an integral quadratic form, sometimes in the literature they call them classic integral forms. The cross terms are even. The cross coefficients are even, so that when you form this symmetric matrix, it's actually an integer matrix.
Right.
Whereas if you have an odd coefficient for a cross term,
we have just one
then
here.
you up with half integers in some of the off diagonal positions.
If it
So
is
they're not integer matrices anymore. But they
So
have
the 15
some of those half-
theorem works only for even.
only for the even ones, right? For the classically integral ones.
Are they associated with 290 theorem?
There's a big brother to the 15 theorem that Bhargava and Hankey proved, but has never actually, there's not actually a proof published in the literature. So there's, the largest number that you have to check is 290. I think, are there 29 numbers in the list? The critical
29
numbers are, there's 29 of them. That's very, very complicated. The proof for the 15 theorem is a beautiful thing. Very only a few pages. The mathematical part is a few pages. Then you have to do a bunch of computer verification of looking for these truants and escalations and stuff. So that's if you push that into the background, the theory is very simple. But not so much for the 290 theorem. That uses all kinds of heavy machinery. So yeah, so she didn't look at, we haven't tackled that at all. We just stuck with these.
Location? Okay, let's thank Lakshika again.